Good morning. Can you hear me okay? Cool. I actually expected less people, so thank you everyone for coming this morning and not sticking too long yesterday at the reception. So yeah, my name is Ignat, and if you heard my other talk on Wednesday, you know that I am a Linux fan. And today I'm going to talk about Linux Kernel Keystore and why you should use it. So who actually knew that Linux has a keystore? Oh, nice. Yeah, so I hope you'll learn something today. First, a little bit about myself. I do Linux at Cloudflare, so we're responsible for the operating system we run in all our production network. I'm passionate about system security and performance, and I enjoy low-level programming like C, drivers, bootloaders, and others carry low-level kernel code. Which brings me that I'm also probably a fugitive programmer because US NSA, I think, banned C and C++ last year around November. So yeah. And why is basically NSA recommends using memory-safe languages, which C is not, and thus the Linux kernel is not as well. And because of that, we're actually going to review what is the problem we're trying to solve, and why do we care about cryptographic keys in your you should care about cryptographic keys in your application system memory. And to do that, let's kind of review the context, the terminology, and operating system address namespaces. So who here knows what a namespace address space is for a process? So a brief introduction. So you run your stuff on the operating system. So imagine you have several processes, and each process has some memory allocated to it, right? So what is the process? When you run a process, what's there in the memory? So you have your main logic, the code you actually wrote and compiled. So your application logic, right? You also may use some kind of shared libraries, or other libraries. They will be loaded into your process address space, so the code will also be there. You also have some data, usually like your global variables or your constants. They will be also in the process address space, right? And your stack. So when you execute your code, you use a stack, and the stack is also located in the process address space. So this is user space. You also have your operating system kernel. So in the kernel space, which is a huge, big, flat address space as well. And in the kernel, you have the kernel core code. You also have the static and dynamic data, like constants and global variables. You also have drivers, and this is why it's kind of really dangerous to load third-party drivers in your kernel, because they kind of get immediate access to your whole kernel address space, and they're not isolated in any way. And you also have the kernel stack or stacks if you spin up your processes. So the idea of address space isolation is that within the address space, like everything can access anything, right? So like you can access whatever you want in user space inside your process, as well as the kernel being a big flat address space as well. So anything in the kernel can access anything. But between the processes, you cannot do that. The operating system ensures that one process cannot access easily without any vulnerabilities, the address space of another process, and also all the user space processes cannot easily access the address space of the kernel. That clear for now? No, sometimes in the morning it's very confusing, but yeah. So now let's actually zoom into the address space of a specific process, and specifically, let's zoom in the data section, right? So what can we get in the data? So roughly, you can get like 3 categories here. So you can have your application internal state, right? when you execute something, you store some temporary computation. So this is in a global variable, for example, or if you use like functional style programming, etc. You also have your user or customer data. If your processes user or customer data, it will also be in the address space. And finally, you might have your cryptographic keys there, right? Because if you encrypt your data, you need a key for that. So, and the problem here, if suddenly your main logic or the library you use becomes compromised, right? Because of the way how address spaces work and everything can access everything, suddenly the whole data section can be compromised, right? But again, not all process data is created equal. What if you have a vulnerability, right, and like your application internal state is compromised? Well, it depends, right? It can be good or bad. So depending on what state it is, if it's like a read-only access, maybe it's not that of a big deal if somebody can read like the intermediate computation you're doing. But if it's a write access, it can lead to further compromise because sometimes data internal state is used to drive the logic of the application, and if the attacker can write some malicious value, they can change the execution flow of your application, right? What if user or customer data becomes, well, this is now becomes really bad. And I mentioned Equifax in my last talk. So if you leak your user or customer data, that's kind of like, that's a privacy leak, and you have to report it, and basically there are a lot of consequences. It is very bad, but still kind of recoverable. But what if your cryptographic keys get compromised? This is already completely game over, right? So now cryptography and PKI and TLS is used everywhere. So if you leak your private key, you can have your identity taken over, like you have full security compromise, and you'll have your data integrity compromise. Who here remembers Heartbleed? Yeah. So for Cloudflare, for example, Heartbleed was the first test that we actually enforce on certificate authorities for certificate revocation. So Heartbleed showed that, for example, certificate revocation lists are not scalable because previously nobody revoked so many certificates at once. So how can you get your basically data compromised, or how can you get a vulnerability in your code? Well, first, your application may be secure and insecure and don't properly process untrusted input, which may lead to out-of-bounds memory access. What it means, imagine you have some stuff in your memory, right? But next to it, you may store your cryptographic keys. And if, for example, and the normal logic of your application should only be reading stuff from the memory, but if you don't sanitize your inputs, for example, the attacker may send malicious input, which may lead the application to actually access the cryptographic key where it shouldn't access it, right? And this is what happened to Heartbleed, basically, right? Because untrusted network input forced the application to read the memory where it should not have been read and dump it to the attacker. Well, you may have arbitrary remote code execution in your code, and there is actually nothing to elaborate here. Like if the attacker controls the execution flow of your application, the attacker can make the application to actually read any memory they want, right? Yeah, and this type of attack we see in the who remembers log4shell vulnerability. Everyone does, probably. So many Jira tickets to come over, right? It's just a simple Apache. We never used Java in Cloudflare, and we still had to patch a lot of stuff for log4shell. Yeah. Buffer reuse. can be a source of cryptographic key leaks. So for example, here's your process or thread stack, right? And let's say you have some main code running, then suddenly you need to encrypt the data, so you call or decrypt the data. You call the decrypt function. That decrypt function takes a cryptographic key from somewhere and puts it on the stack, for example, right? So the idea, and if you just finish decrypting and exit the function will exit, but the key will be on the stack, right? And for example, the next function, which might be totally, safe from your perspective, will have access to that key. And for example, if it's a logging function, you may accidentally log your cryptographic key, and so by leaking it. So this is why all these security requirements for security coding requires you to zero out memory with cryptographic keys after you've finished with them. Yeah. So as I said, yeah, you need to zero memory after key reuse on both stack and heap. So I showed you a simplified version on the stack, but on the heap you can get the similar result, right? If you don't zero out the memory before returning the memory to the heap, you may get in trouble. But it's actually easier said than done, right? It's very challenging to do this in a garbage collected languages. Try to doing it in Java or Golang, you don't have direct access to the pointer, and by the time you're finished with the key, it can be copied all over your address space. Finally, you may leak your keys due to bugs, right? Say you have a segmentation fault, so improper logging, core dumps. If your application crashes, it may produce a core dump, and the core dump may contain your cryptographic keys. GDB and various or ptrace debugging techniques, right? So how do we actually prevent accidental leakage of cryptographic keys from your process address space? Well, let's just not do bugs. Right? Let's just fix all the bugs. So I don't understand why people write bugs, so let's stop writing bugs and we'll be good, right? Well, yeah. And probably we can't fix all the bugs, so technically we can't have a perfect software. But how can we actually prevent at least a class of a problem? How can we actually prevent leaking at least cryptographic keys from our process address space, because they're kind of the most value to the attacker? And what the typical approach some software takes is a so-called agent model. So instead of one process that you used to have, you now have two processes, right? And what you do is actually that other process will also have a data section, and you move your cryptographic keys from your main process, which is network facing usually, to the other process. Yeah, and also you write some simple logic, I call it crypto logic, and which actually just implements a very streamed down, well-defined interface between the main process and the agent process. So the main process can ask the agent process to perform cryptographic operations on behalf. Yeah, so now we have two processes, main and helper agent, and due to the address space isolation enforced by the operating system, the main process does not have access to cryptographic material, right? Now, it's kind of safe. Even if you have a bug in your main process, it can't really easily access the memory with keys. And the main process communicates with the agent through a very slimmed down, strictly well-defined interface to perform cryptographic operation. And therefore, the main process is this very code-rich heavy, so it can process untrusted input and usually network-facing, where the agent process never processes untrusted input, only the request from the main process, and is usually never network-facing. So you can think of an agent process as a software security key, right? Somebody here uses YubiKeys? Yeah, good. So think of it like a cheap version of a YubiKey where your key is stored in a dedicated process. And there are examples of that you may be using every day already. So SSH agent, who uses SSH agent? Yeah, this is an agent, and if you use GPG, which I don't recommend, so you may use a GPG agent as well, right? So it all works good, but there are some drawbacks, of course, right? So you need to develop and maintain, instead of one program now, you need to maintain and develop two programs or processes. You need to actually design this well-defined interface. Like, who can say they are good at designing interfaces, right? So it's tight enough not to be exploitable. You need to add the communication layer between two processes, so you need to use Unix sockets, shared memory, whatever, some kind of operating system primitive for IPC. And you also probably need to somehow authenticate and enforce ACLs of the main process, because the agent process contains your cryptographic keys. What prevents other malicious processes on your system talking to it and performing cryptographic operations on their behalf? So it's kind of a hard problem, right? So this brings us to Linux kernel key retention surveys, or simplified, like just Linux Keystore. So the idea here, instead of this other process, why don't we just replace it with the Linux kernel, right? It's a separate address space anyway, and our well-defined interface will be system calls. System calls is a great, well-defined interface already, so let's just reuse it. And this is what Linux kernel key retention service does. So it stores cryptographic keys as kernel objects. And it was actually initially designed for sharing keys with the kernel services. So for example, if you use Linux disk encryption, you might be using Keystore already, so it's a way to share a cryptographic key from user space to the kernel, so the kernel can encrypt your disk. But now it's kind of like it was extended to be used by user space programs, so user space program can manage their keys. And the benefits of it is similar to agents. So the keys are stored outside of your main process address space. You have a well-defined system call interface to access and use the keys. Because keys are kernel object now, they have associated permissions and ACLs. So you can set permissions like you set on a file on a key. And you also, they're subject to LSM hooks. So like if you use SRELinux or other, you can write almost arbitrary policies for accessing your keys. And the nice thing about it is that now the key lifecycle can be implicitly bound to the code lifecycle. So the key auto-destruction, that zero out memory after key use, will be enforced by the operating system when a process terminates. And we'll see. And surprisingly, it has relatively good documentation in the kernel docs. So in order to understand the kernel keystore, let's define some terminology. So kernel keystore operates on keys and key rings. And a keyring is an object which can contain either key rings, or it can contain links to a keys. So it's kind of like this tree-wide structure, similar to file system. The only difference is, for example, a key may live in several key rings at the same time. So, for example, a key is an object which contains actual cryptographic material or some kind of pointer to it. So in kernel keystore, keys can also be backed by hardware devices, for example, like a YubiKey. And they can be read and written to if you have permission. And you can use keys to perform cryptographic operations. There are different types of keys. We will dive into different types of keys later. So they can be user, logon, asymmetric, encrypted, and trusted. And they're kind of similar to a file on a file system, but the difference, as I said, they can be linked to several key rings at the same time. So key rings, it's a collection of keys. They contain so-called links to keys and other key rings. And key rings implicitly enforce the lifetime of a key. So if a key is not linked to at least one key ring, it is automatically destructed by the operating system. And key rings can be explicitly created by users or applications, or they can be implicitly created. There are special keyring types called thread, process, user, and session. And yeah, as I said, they enforce the key lifetime. So if all the key rings are destroyed, which have links to a specific key, the key is also getting destroyed. And they are kind of similar to a file directory in a file system. So far clear? No? Yeah? Let's see an example, right? By the way, this was copy-pasted from a real terminal on a real system, so consider this as a demo which never fails. But and you can actually then go back and copy-paste all these commands and try it on your Linux system yourself. So with this command, we're actually creating a new custom keyring and linking to my user keyring. So I will explain the user keyring later, but so far we just create a new keyring, and the return of the command is the so-called serial number, the unique identifier of the key or keyring object in the system. Now, we can add a key to that keyring and put some secret into it. So like a secret is in red, so let's store some secret in the keyring, and then we can actually see what my user has access to. So this will show you the key hierarchy. So as you can see, at the top of the hierarchy, I have my session keyring, then my user keyring, then my custom keyring, and my custom keyring contains one key called my key, which has some secret attached to it. Yeah, and everything is designated by serial numbers. So you can see like my custom keyring and my user key having these serial numbers. And also, since I have access to that key, I can actually read that key back and see the secret attached to it. Simple, right? And quite useless. Like, let's see a better example. Let's imagine we have two users on the system which are not related. They're not sharing any groups, nothing at all. So totally two different users. So we can actually do secret sharing between the users via keyring. So let's say I add a new key to my user keyring with a secret. So what Alice adds, like Alice and Bob. Alice adds a new secret to their keyring. What Bob can do, Bob can create a new custom keyring called from others, and Bob can also set permissions on that keyring, which means that hex number means that others can write to the keyring but not read from it, which is cool. And the Bob then somehow communicates the serial ID of that keyring to Alice, and what Alice can do, they can move their secret to the Bob's keyring, right? And now Alice doesn't have access to the secret anymore because it was moved. But Bob can actually read the key because it's in his keyring. So yeah, and if we print all the keys Bob has access to, so it has the keyring, the key shared by Alice. So like you see, no similar groups, nothing, no IPC. It's just like one user can send the key easily to another user with no problems. So now let's review what can, like the power of Keystore also comes with the implicit keyring types. So we have the process keyrings, which include session, process specifically, and thread keyring. So the session keyring is shareable by the current process and all the child processes. The process keyring is implicitly bound to a specific process, and a thread keyring is private to a specific thread. Imagine you can run, for example, an Nginx web server where one thread processes one domain, and each domain has an associated like private key, and like one thread cannot access the key of another thread, which is really cool. You also have users keyring. So with process keyring, like actually the lifetime of the keyring is implicitly bound to a process somehow. With user keyring, the lifetime of the keyring is bound to a specific user. So we have the user keyring, which is shared between all processes with sharing the same user ID. And we have user session keyring, which has some specific semantics, not important for the talk, but very similar to user keyring. You also have a special type called persistent keyrings. The idea that persistent keyring, they don't get destroyed when the last process with a specific user ID exits. So they're usually useful for like non-interactive tasks like cron jobs, where a job runs periodically and it needs access to some key. So it cannot be bound to a specific lifetime of a process of a user. Instead, that key just have an associated timer. So if no process accesses it for a specific amount of time, it kind of gets destroyed. So let's see. I mean, you will get the slides, but if you want to move further from the back. So let's see an example of a session keyring. So now in this example, I'm adding a secret to my session keyring. And just for the record, imagine me SSH'd into some machine. Right? So I can now see that the secret, I have access to the secret, and the secret is linked to my session keyring, right? Now, just to ensure the key gets automatically destructed, I will put a BPF trace probe on a kernel function which is responsible for key destruction, for the user destroyed key, right? And what I do on my machine, I just exit my SSH session. And immediately we see that my probe works and like the key which I created gets automatically destroyed. And the reason is because my SSH session is a process and my session keyring was bound to that process. The moment I exit my session keyring was destroyed and all the keys linked to it were also destroyed automatically. And I can check it, I can SSH back, and I can see I don't have the key anymore, and I can see that the session keyring has a different ID because the old one was destroyed, and when I logged in, the operating system created a new session keyring for me. So this is the power of keyring, that by selecting the appropriate keyring time, you can ensure the keys will be securely destroyed when not needed. And even if your application crashed, so you can use this from your Java application and you still don't need to care about zeroing out memory, right? And even if your application exits abnormally, so your cleanup code was not able to execute, the kernel will still ensure that all your cryptographic material will be destroyed. Cool, so let's review the various key types I mentioned. So the simplest key type is a user key, which is just a buffer in the kernel containing some secret. So a process can put the key into the kernel keyring, and for example, either the same process or another process which have access permissions can read that key back into the process address space. We also have a logon key, which is a slight modification of the user key. The difference is a process can put a logon key into the kernel keyring, but the logon key can never be read back. And this is mostly used for sharing keys with internal kernel services like disk encryption. So for example, if you're running a relatively modern operating system distribution, you may notice that if you use disk encryption, your keys are actually logon keys shared with the kernel. So if you run this command, you will see, if you see the logon thingy, then that means your disk LUKS setup used actually the kernel keystore to share the key with the kernel. We also have asymmetric key types. So you can, for example, put an RSA key inside a kernel keyring, and other processes do not have to read the cryptographic material key back, but they can use the handle of the key to perform cryptographic operations. So for example, you can put a private key and you can decrypt something with it or sign something with it. So here is a simple example. For example, we can generate a random RSA private key. We need to convert to PKCS8 format because this is how kernel understands private keys. We can put it into the kernel keyring, and then, for example, we can ask the kernel to sign something with that private key, and we can then use OpenSSL actually to verify that the signature is correct. We wrote a blog post about the Kernel Keystore, which you will find all the information available here and more. And one of the ideas there, we have a toy patch to the SSH, OpenSSH software, where you can actually replace the SSH agent with the Kernel Keystore. So you don't need to run with a patch, you don't need to run an SSH agent anymore. You can put your SSH keys as asymmetric keys in your kernel, and then the OpenSSH will just use the Kernel Keystore to do the SSH sessions. Okay, so this is all about the Kernel Keystore, but Kernel Keystore turns out to be a really great building block in big enterprise setups, clouds, and you can build a really sophisticated key management system. And the question is, of a good key management system, how can we actually provision application keys without cryptographic materials ever touching user space? So remember, we have the process address space, and if there is a bug, like the memory could be read, right? So if we even like temporarily put a cryptographic material in the process address space, we have this small window of opportunity for the attacker to actually get it. So what can we do? Turns out there are more types of the Kernel Keystore you can use. One useful type is called an encrypted key, for example, which works the following way. For example, the kernel keyring already has some kind of a key provision somehow there, so we call it a wrapping key. So the process may have access to an encrypted blob where a key is encrypted by that wrapping key, and that process can actually put it inside the kernel, and the kernel will automatically decrypt that key with the wrapping key if it's available. And when same process or another process tries to read that key back, it will be wrapped by the kernel automatically, so the plain text cryptographic material never leaves the kernel space. But you may notice you have a chicken and egg problem. So how do we then provision the wrapping key, right, securely? So on its own, it's not very useful. The one thing, there is also like a thing called trusted keys, where you kind of can replace the wrapping key with the TPM, and all modern laptops and servers should have a TPM these days. So you have this wrapped key, and it can be wrapped to a specific TPM on your machine. So when you basically put it inside the kernel can use the TPM to actually unwrap. And again, if you read it back, it will be wrapped again. So this way, the plain text cryptographic material never leaves the kernel space. Although going to the TPM is not quite very useful, and TPMs are slow, and some TPMs easily break when you create too much requests to them. So a combined schema is possible. So imagine you have some kind of process which needs some kind of key or access to a key. So you can also do like some kind of provisioner, and then you have like an HSM running somewhere. It can be a cloud HSM. I don't know, like people use in the cloud, like AWS, key management services, whatever, some kind of root key, which has access to a root key. So that root key can be wrapped to a specific machine's TPM and sent to the provisioner. The provisioner will actually instantiate that root key in the TPM, and the root key will be unwrapped, so kernel will have access to the cryptographic material. And then the same cloud HSM may send some kind of wrapped key to a specific process, like a process-specific key, which can be unwrapped, which again can be instantiated in the kernel, and the kernel will unwrap that key with the root key. So you go only to the TPM once per boot, for example, to unwrap the root key, and all the other applications' keys are wrapped to that specific root key. But again, this is better, but it has some problems, right? Applications now never see the plain text cryptographic material, but applications are somehow responsible for contacting the centralized KMS HSMs. right? So you need to modify your application code to know how to reach that centralized HSM. You have to configure your application that it knows the URI endpoints, where should it reach. You need to use some kind of SDK maybe, et cetera, et cetera. So it's a little bit of a big overhead, right? And you have also little administrative control of created kernel keyring objects, right? If application instantiate its own key with invalid permissions, that probably can lead to a problem where other applications can read that cryptographic material. And KMS and HSM needs to somehow authenticate each requesting applications, because even in wrapped form, we only want to give a key to the application if it's, like an authentic request. This brings us to another useful Linux kernel keystore interface. So far, we've been adding keys via add key system call, which just gives a process the ability to send the cryptographic material wrapped and unwrapped to the kernel somehow. But there is another interface called request key, where a process doesn't send any cryptographic material. It just requests the kernel to provide it. And of course, the kernel does not know how to properly contact an arbitrary HSM, which is specific to your infrastructure. But if the kernel cannot satisfy the request, it calls a specifically dedicated kernel program. And you can write this helper program to hook into your KMS subsystem. So this is roughly how it works. So instead of sending some wrapped information, the process only needs to know its key identifier. What is this? Let's say we have a key which with the label cloud app key 1. So what the process does, it sends a request key to the kernel, and the kernel creates a small placeholder for it. Then the kernel calls out back to a specially designated user space helper program at the specially defined path. And this program can, there is a default implementation in many operating systems, and it's quite modular. So you can write extensions and modules to it, where you can have it as a router. Depending on the key ID, you can forward the request to different backends. Let's say if we requested a cloud, you send the request back to your cloud HSM, right? And your cloud HSM basically satisfies the request, so it sends the key material back to this special agent, and the special agent instantiates the key on behalf of the application. And application then can use that key, depending on its permission. So a request key advantage is it provides a single centralized operating system API to request key for applications. There is no KMS, connection strings, URIs, etc. for the application to maintain. Only one system call, request key, give me my key, right? And the labels are just a free-form ID where you can design yourself specific to your KMS. And it's fully decoupled from, the application is fully now decoupled from the key storage backends. And it's a more secure way to instantiate keys in the kernel. So that specific helper program, which is spawned by the kernel, have specific permissions to instantiate these keys requested by application. No other malicious program can do it instead of this helper program. And this helper process can perform additional security checks. It can, for example, authenticate the requesting application. It can do check the user group ID. It can enforce arbitrary policy. When it instantiates the keys, it also can enforce arbitrary access control permissions on the instantiation key. And this helper process, as I said, can support multiple storage backends. And from the KMS perspective, now you don't need to fully authenticate each process requesting a key. You need to only authenticate this specific helper process somehow. And as I said, these backend connectors can be actually written in any language. So because it's a user space program, you can write it on C, Python, Go, whatever. It's up to you. So yeah, so with request key system call, the key management and distribution becomes the core service of the operating system. So I think this is all I wanted to deliver for today for this slightly complex topic. These are some useful links to the kernel documentation about the kernel keystore, various kernel key types and keyring types, and all the material presented here and even more with some examples, and the patch to OpenSSH is presented in our blog post, which is the last link. It also includes a test code which illustrates if you leave your key on, accidentally leave your key without zeroing on the process stack, how a specific function can access it and accidentally leak it if you're interested. Yeah, thank you very much, and probably if we have any questions, I'm happy to answer them.